So I started doing some stuff where I had to dig into AVR flash memory, and eventually got to the point where I thought that it would be might be of interest to the group. And um, my ultimate goal is kind of over the horizon, and but I'm going to be planning a talk on what the project is that I'm working on that's motivated me to learn everything there is about the flash, and especially the idea of uh, an Arduino modifying its own flash memory on the fly. Um, so anyway, so this is going to be the first part of delving into that, and I'm already planning a second piece of this. Um, and then the last part will be in terms of the application, what I'm actually trying to do. So I'm just going to quickly go through how Flash works, and time check. Okay, so it's 13 till. I want to just really zip through this so that we have plenty of time to talk and not burn up the whole meeting time. So the way flash memory works, it was cooked up by a guy at Toshiba a long time ago, is it stores an electric charge on an insulated gate in a field effect transistor. And it uses a second gate structure to control the cell. And while the charge is in the gate, it's just kind of sitting there as an electric charge that doesn't go away quickly. In fact, it takes literally years, many, many years, for that charge to go away if you don't do anything to it. So when the charge is in the transistor, when it's not in the transistor is considered, the cell, the memory bit, is considered erased, and a convention was established from the get-go that might have its root with some kind of technical rationale that makes it extremely hard to do the other way. But that convention is such that an erased cell without a charge is considered to be in a logic high state. And when you put a charge in the cell, you're changing it from high to low. And this gets to the root of some of the problems that we have thinking about flash memory, especially in an Arduino context, most especially to do with fuses. Because when you set a fuse on the Arduino, you are changing it from a 1 to a 0. It's an active low scheme. And flash memory within an Arduino context is by definition fast enough to keep up with the processor. The 328 that I'm focusing on runs it up to 20 megahertz, so the cycle time is 50 nanoseconds, and the flash memory will feed instructions out of flash memory into the processor fast enough to keep up with it. So by definition, the read is at least as fast as 50 nanoseconds, and maybe faster. The write speed's a lot slower, and the erase is slower. And I told myself I was going to actually measure the speeds because I've been doing a lot of writing and erasing and stuff, and I didn't get around to setting up to actually time it, but I'll have that information some other time, just for grins. All I can tell you is that erasing the entire chip is a noticeable.
Does it matter whether you erase to 0 or erase to 1?
You can only erase to ones. Okay, that's a good point. In fact, it's literally you can't write a bit from a 0 back to a 1. You can only write operations are only capable of adding a charge to the transistor, and that action changes it from a 1 to a 0. And as long as you're adding 1 bits, you can write to that flash all day long, and there are systems where you can
0 bits.
efficiently leverage the fact that you're just adding zeros. But as soon as you want to go back from 1 to a 0, the only way to get back is with an erase, which is taking the charges out of an entire group, as we'll see in a second.
I've written code that kind of looks and says, I want to write a byte to this block of flash, because you can only erase them in blocks. And so, if it wants to just write a value, you have to optimize it to prevent a lot of erases. You can say, well, do I need to write any ones? Yeah, but do I need to write any ones where there's currently zeros? And that's the thing that requires you to erase the whole thing.
Right. So there are some clever systems where you can structure it in such a way that where you can go a long way without being forced to erase a page. Some real basic characteristics of the flash in the AVR families. They say that the charges will hold up such that there will be only a 1 part per million error in the read or write accesses, well, I guess it would be read accesses, within 20 years at 85 centigrade and 5 times that long at room temperature. The other thing is that the erase process and or the write process, but I'm not sure, I think write is kind of a first cousin to erase. It degrades the transistor. And after the guaranteed 10,000 cycles in the case of this chip, all bets are off as to whether or not it's going to properly erase, and the chip is going to properly behave after 10,000 erase cycles. And I personally think that going back to the endurance, that if I was going to make something and I was going to expect someone to use it for several years, I wouldn't bet on that 1 part per million. I mean, that's a statistical thing, right? So some of your devices are going to be on the wrong end of the bell curve, and they're not going to cooperate with that. And so if you had a lot of devices out there for several years, and it was a critical application, I think you'd be wise to actually confirm that that the system was, that the bits were, the 0 bits were where they are where they should be. So the way flash is addressed in the Arduino chip is in 16-bit words, and this gets to the fact that the primary usage of the flash memory is for instructions. Constant data is also stored in flash memory quite often, but it can only be accessed a word at a time, 16-bit word at a time. And so that's the granularity, the instruction, the load program memory instruction for accessing the flash is only capable of doing 16-bit operations. So if you want to do bytes, then you're going to byte swap, and you're going to accumulate 2 bytes worth of data and then write the 1 word. Or in the case of a read, modify, write, you're probably going to try to optimize like John was talking about. The groups of words John mentioned earlier called pages, and on the 328, which is that's the main Arduino, the chip that's in the Arduino Uno, Nano, and Mini. So it's the really popular one. They're 64 words long, and that page size varies. Other kinds of chips will have a different page size, and that's the minimum amount that you can erase at once. So when you go to add something new to the flash memory, your one and only choice, if you have to erase, is to erase 128 bytes at a time as 64 words. And further, with the Atmega, the pages are in 2 sections, one called the application section and the other called the bootloader section. You don't have to have a bootloader section, and there are bits there are fuses that allow you to change the size of the bootloader section. Some chips don't even have a distinct pair of some of the AVR family members don't have the distinction of the two kinds of sections. So, one of the interesting things is that because the finest grained access to flash memory is a 16-bit word, you don't need any addresses. You don't need byte addresses with low order 1 bits. So they've optimized the instructions so that the encoding of addresses of flash memory addresses, such as branch destinations, for example, they are 16-bit word addresses. And the interesting thing is that allows accessing 128 kilobytes of flash. Of course, the Arduino 328 only has 32 kilobytes of flash, but some of the other chips, in particular the 1284, have a full 128K. Some of the Arduino Mega families have more than 128K bytes, and they use extended extended load and store instructions and some really evil, well, in my opinion, ugly tricks to do with extra addressing bits that are hiding out in special registers and so on. But the kind of logical limit of the 328 family is 128. The group of AVR chips of which the 328 is a member is 128K bytes.
Some of the old bootloaders for 1284s had bugs where they would mess up. I ran into problems in the past with when an application hit about 64K where they were not doing the math right. The bootloader was corrupting it.
Yeah, that's a shame. So the application section is for application code, and the bootloader section is primarily used for cases where you are going to conveniently reprogram the chip without using a chip programmer that plugs in and is an outboard gadget. Where most of us that use Arduinos are familiar with the little tiny program that's in the chip that can talk via the serial ports to take data in and use it as information to redefine the flash. Well, so the interesting thing is that with the 328, that's the only code that is, let me put it this way, the instruction for changing flash memory is ignored when it executes in the application section. It's a no-op. The store program memory instruction is only able to store into flash memory when it's executing in the bootloader section. And most of the common bootloaders, certainly the serial bootloaders that we're used to using with the Arduino, have not. They're written to save every bit. I mean, they are especially the OptiBoot bootloader that's real common in some of the Arduinos is ultra optimized code, and so they don't have anything abstracted out as a utility function that application code could use to call up into the bootloader section and say, hey, please modify these locations of flash memory, such as for storing data. And in addition to that, it's common with Arduinos for some of the configuration options to be set such that the application that even if there was code in the bootloader that was going to execute with the application, a lock bit set such that it can't execute the SPM instruction. So one of the things that I had to figure out was, oh yeah, right. So by default, even that avenue is closed off. Anyway, then there are a few special regions. Every AVR chip's got a signature, and I don't know if the length varies, but in the case of the 328, it's 3 bytes long. And there's a 3 byte sequence for the Mega 328P in a 20-pin DIP package, 28-pin DIP package, and there's a separate signature for the one in the 32-bit TQFP package. There's a third one for the 328P in the QFN 32 package. So, also well, it basically, it boils down to the intersection of the type of chip and the packaging. It's possible that they reuse some of the signatures where the package is different, but it's absolutely and totally pin compatible. I'm not sure, but then there's a set of fuses that set chip parameters, and I think Shane was talking about having to reprogram his AT-Tiny to use an external resonator, and let's see, I've already covered that.
You can tell AVR to ignore the signature.
Oh yes, absolutely,
If
dash
you're
F,
using an old
right.
version of
Yep.
AVR dude and it's
Absolutely.
a new chip and it doesn't
Sure.
like it.
Yeah, you can do that.
You have to really know what you're doing though to see do a little bit.
And, yeah. So for writing, there's a store program memory instruction, and another basic thing to know is that with the Mega chip, the flash memory is in a different address space than the static RAM. Even though if you go read the fine print, turns out with a lot of the chips, one is mapped into the other address space, but let's not go there right now. But generally speaking, when you access location 256, if you're fetching a data byte from location 256, you're getting it out of that address in the static RAM area. But if you're fetching using this SPM instruction from address 256, it's accessing the flash memory. So there's a specific instruction for storing, and then also an LPM for loading flash addresses. They ordinarily can access one 16-bit word at a time, but there's a special version that will automatically write an entire page from a special internal temporary buffer, and you can load up that temporary buffer with a page worth of data, and it's separate from the static RAM. You don't have to use a byte of static RAM memory for this. It's a magic extra internal buffer. You load that up, and then with a single special SPM set of addressing modes, it writes the entire page of flash.
And does that occupy the processor for some hundreds of cycles? while it's doing
Yeah, and that's one of the things that I expected to get around to having measured, so I could have told you, and that takes
Okay.
X milliseconds, but
Is there not a way to do that asynchronously where you can say do it?
yes, absolutely. And in fact, there's a specific interrupt vector for being interrupted, but that gets you into the can read while writing and cannot read while writing, which is a part 2 topic. Here are some references. The Wikipedia flash memory page is really good about how flash memory came about, and a lot of things about the different flavors of it, most especially the very high density flash-based disk drive replacements that are out there. The Wikipedia page for the AVR instruction set is, in my opinion, much more useful for figuring out the instructions than looking at a handful of microchip or Atmel documents, and especially getting a sense of which versions of AVRs do what. And then the 328 data sheet's got all of the details. There's some additional slides that will be on in the meeting archive that have some additional things that I'll go into in more depth with part 2. Questions?
So you mentioned that there was a way to prevent anyone from writing Flash. Does that apply to the bootloader as well?
Absolutely. In fact,
If you set this date, you can no longer.
You can arrange to cut off your access to the chip completely, and your only option, your only way out of that is to erase the chip with a special process. And so obviously by erasing the chip, you're not going to discover what was in it before you were forced to erase it. But you can also turn on and off privileges, like you can say the code running in the application space can do this but not that, and same for bootloader with respect to different
Application
features.
can never write.
But the application, on the 328, code in the application section cannot write, except what you do is you put a function up in the bootloader section and you call it, and on your behalf that code can execute, and because it's in the range of addresses that the chip knows is in the bootloader section, it does.
Can the application code write to the temporary buffer?
No.
No.
That's used, the writing to the temporary buffer also uses SPM.
And the bootloader section is configurable. You can have no bootloader section as part of the fuses.
Right.
So,
Yeah. Yep. Any other questions?
were you going to cover maybe in a different section, like the difference with the Flash versus EEPROM, or why you were using, because the EEPROM's a lot easier to use if you're just writing a few bytes here and there.
Yeah, but it's also unbelievably slow, just mind-boggling slow for writes, and it's also really small. And
Right.
yeah,
There's pros
So-
and cons if you
Right.
if you only need a few bytes.
right. Yep. Let me turn this off.